All right. Okay, so back to our topic, populations, and the red-cockaded woodpecker is an example. By the way, here's the bird I just caught in the house. It's a Carolina wren. It's free now. So just reminding you here of what what we're dealing with here is a endangered species of bird called the red-cockaded woodpecker. It depends on longleaf pine and other pine species. They're really common, but what's not common is the habitat type they need. And they need old trees, 70 years old or older, and they need habitat that's open. So they can't be a dense forest. It can't be a pine plantation. It's got to be open and kept open with fire. So in other words, it's got to be natural. So the red-cockaded woodpecker is in the southeast United States, and it's an endangered species, but it's recovering slowly. Why is it recovering slowly? Well, because the habitat is extremely fragmented. Most of the southeast United States has been developed. There are small areas that have been reserved. But just because an area is set aside, protected, doesn't mean it's actually good red-cockaded woodpecker habitat. So there's a few places like this right here, in southern Georgia, Silver Lake Wildlife Management Area, that is dedicated to conserving the habitat that would be here, would have been here before that area was highly modified. So if you zoom in here, what you see are pine and oak dominated woodlands here. And as you can see right here, see those straight lines? Those are pine plantations. That's longleaf pine. And this is sort of the bread and butter of the southeast United States for income for a lot of people. I'm sure for this, I assume that they own this. These are pine plantations. It's sold. And this is what goes into, sort of feeds into lumber. It's exported as well. These are really important economically. There's a lot of pines there, but they don't get to grow. They don't live to be not allowed to live 70 years. They're cut down after about between 20 and 40 years for the lumber value. And down in here, so woodpeckers won't nest in them. They couldn't if they tried anyway. The trees aren't big enough, and they're just totally wrong at all for most biodiversity. It's not there. But outside, you see, I can zoom in right here, and you see a sparse. See how the forest is sparse. If you were to zoom in even further, you'd see this picture was taken actually during the winter, but the vegetation is very sparse in there. So this is what red-cockaded woodpeckers need. Now, if you look at these trees, you're seeing shadows here, but they don't really look particularly thick in diameter. However, what's happening here at this reserve here, this wildlife management area, is they are protecting this area, and so over time, it's going to develop into better red-cockaded woodpecker habitat. Right now, they have I don't know how many individuals, but it's not enough. So if you look at their website and see what they say about this, this is not their website, but it refers to the Silver Lake Wildlife Management Area, over 8,000 acres. It's a very large area. They use controlled burning, and they are right now. There's 21 red-cockaded woodpecker family groups. Now look at that, 21 red-cockaded woodpecker family groups. That's the interesting thing. So it's not 21 red-cockaded woodpeckers, 21 adults. It's not even necessarily 21 pairs or 21 nests. It's 21 family groups. Okay, so, and then eventually they want to grow this to 50 family groups. So these family groups, these are territories. So if you want to increase the population of red-cockaded woodpeckers, you got to increase the number of family groups or territories. Family groups don't like other family groups. They exclude them. But we need more family groups. So how does that? Family groups have to come from somewhere, right? Which means that as the population grows, sons and daughters leave and go somewhere else and start their own family group. But they need the trees to do that. Sure, my okay, so now is this enough? So we have hundreds of little conservation efforts all around the southeast United States, Some are really significant, like this one, the Silver Lake, and others are really small. Does the whole thing, is this going to save the red-cockaded woodpecker? Well, it's hard to tell. You don't know what's going to happen in the future, so what you have to do is model it. And this is the point in the class we're going to introduce modeling. Modeling is, I just want you to sort of come away with the way of thinking about modeling rather than the details of how modeling is done. I can tell you this is the way science is done now, is with modeling, but it's always been done this way. But in conservation, you do modeling, statistical modeling, simulation modeling, and this is the way it's done. There's the field work, of course, but there's the modeling, where what it is you create an artificial population in the computer, and then you grow it. You see how fast it grows and what happens to it in the future when you go in and manipulate it, like birth rate, death rate, dispersal rate, frequency of hurricanes hitting it. So it's an artificial system that you manipulate, and you hope that you've created this artificial system to match the real system out there in nature as best you can, because you can't go out in nature and do experiments with red-cockaded woodpeckers. It's very hard to even measure their growth rate, how many eggs they have, and so on. So by the way, this is not unusual. This is what's done with everything. So weather models, your weather forecast comes from an artificial system that's created in a computer. It's run, it's simulated, and then that's where you get your percent chances of rain. You look at a bridge that's built. The Tappan Zee Bridge was dropped and then torn down. They built a new one there. That new bridge was modeled before it was ever put in. How does it respond to wind and increasing weight and all these dynamics that you have to do that? So modeling is very normal and natural. It's just now it's just more sophisticated and lots more people can do it when you have better computer power. So red-cockaded woodpeckers, what you want to do is you want to see, is what we're doing enough? Is it good enough? So as a population, how large, even more importantly, is how large does the population need to be in order to be able to sustain itself in the future and not go extinct? How large? Well, instead of talking about individuals, it needs to be N of this size. He's talking about we need to have X number of family groups or territories. So with that, let's take a look at the paper we're going to use, which is by Walters et al. Down here, the readings. Here's Walters et al. And this is under population viability analysis. Here, read the abstract introduction, make sure you understand the results of figures 3 and 5, and try to also understand what's shown in figure 1. I said try. This paper will be is beyond the level of this class. But what you got to start somewhere. So if you're going to have a profession that's connected to conservation biology, you're going to eventually either be doing modeling or you're going to have to interpret models. So we got to start somewhere. Let's just start here. Here's the paper here, and here's the study. This is how it's done still now. The paper's 2002, but it's still it's nothing. This is the most recent paper where I've actually seen a population viability analysis. So here is what is basically their modeling here is, so you start off with, you're going to give the population a certain number of territories, family groups, and then let it run in the future. So what it is, let's say 100 years, but really, I guess you can say it's really supposed to be 100 generations. But so you let it run for oftentimes a century, 100 years, or 100 generations, and you see how many, when you did that, what percent of the time, because you keep simulating it over and over and over again, you started over again, different things happen randomly. What percentage of the time did that population overall go extinct? Okay, so you start with 25 territories, like 49, 100. Keep in mind that, yeah, it'd be really nice to have 500 territories of red-cockaded woodpeckers in an area in Georgia, but it doesn't mean you're actually going to have them. You may never not have enough habitat to support that, or 250. But let's just say you have, 50 territories. You think you can get there with that. The next thing you got to do is you got to ask the question about so you have 50 territories. Well, 50 territories spaced out in what way? It's another thing I want to introduce in this class is the fact that density, number of individuals in a landscape, also depends on, well, depends on the spatial, how they're distributed. So here's this area here. How large is this area? Let's just measure it here. I'll look at kilometers. By the way, a kilometer is easy for us to remember because the University of Rhode Island Kingston campus is about approximately 1 kilometer by 1 kilometer. You don't include the farms around it, like East Farm or like Peckham Farm. So our campus proper, the main part of the campus, is 1 kilometer by 1 kilometer there. So that's easy to remember. So kilometer here, how big are we talking here? So here's a radius going out, and there's about 1 kilometer right there. The Northwoods, I'd say, could fit right there. Our campus, the URI campus, could fit right there. If you're a bird, you know, birds can fly, right? So flying 1 kilometer shouldn't be a problem. And if birds are nesting here, so the question is, over this landscape, how many red-cockaded woodpeckers can you fit into this landscape? The better question to ask is, how many family groups can you fit into this landscape? Remember I said that the family groups don't like each other. They exclude each other. Well, that may not be how much of a problem is that? Well, it just depends on depends on the nature of the habitat. How good is the habitat? So if it's a really, really high quality habitat, then you might be able to pack in a lot of territories here. So I'll just make some here. So imagine this is really high quality habitat. So you can make a lot of different territories. You can pack them in kind of like this. You can really pack in the territories. Imagine they look like this. And these are family groups. That is, they are territories. Imagine, I'm not going to draw all of them here, but imagine that the habitat is such high quality that that size right there is all they need. And then, so more territories means more birds, which means a less of a chance of extinction in the future. Now, on the other hand, it could be that the habitat is so poor that one family group needs a larger area in order to survive. In which case, you know, you might see something like, you know, like that. So if the bird's family group needs a larger area to survive and to find enough nests, then you're not going to be able to pack many territories in this area. So with that, this introduced this part of conservation biology. So it's the modeling approach. So we have to, over time in the future, the red-cockaded woodpecker population in Florida, in the southeast United States, is going to fluctuate. But we want it to go up. But things happen, like Hurricane Ian just happened, and other hurricanes happen. You can count on one hurricane a year somewhere in the southeast United States that's going to cause a lot of habitat damage to forest. And then maybe a major hurricane every 10 years. And then other things happen. Droughts happen. Uncontrolled fires might happen. Development happen. You get a political change, and maybe a new administration is not as friendly to the environment. Anyway, things happen. So the question is, how large do populations need to be in order to conserve the species? So the species is listed as endangered. You want to be able to get them up to the point where they're no longer endangered, but only threatened, and then eventually get the population up so that it's no longer listed as threatened. You can say they're on their own now, and the population can grow and sustain itself into the future if they have enough habitat to do this. So one approach is to estimate a number. The number is the MVP, not most valuable player, but minimum viable population size. What size does my population need to be in order to be able to say that this population is been successfully conserved and it's not going to go extinct in the next 100 years? Very unlikely. Viable means it just can sustain itself without intervention. Just think of some really common species around here, like American robins. They're going to be around 100 years from now. They're going to be around 200 years from now, most likely. The population is very large. Minimum means the smallest population, viable like that will persist for, and you set a number of years. And oftentimes you'll hear it called years and sometimes generations. 100 500 years with a certain threshold of certainty, kind of like a weather forecast. So 95% level means that 95% of the model runs produced a population that was still going 100 years later or 500 years later. That's what you want. So you want to have a high probability of a population surviving well into the future. But you need to know what do you start with? If you start with a really small population in your model, it's going to crash. You can start with a really large population in your model, but is that realistic? Will you ever be able to get that population up to that level? Remember how difficult it is to get the red-cockaded woodpecker numbers up. Slow reproducers, picky their habitat preferences, and there's just not a lot of the kind of habitat they need left. So to estimate the MVP, you do a PVA, which is a population viability analysis. Typically what you do is, if you're doing conservation biology, is you hire or you bring somebody in to do your modeling for you and you include them on the paper. But it's a simulation model, kind of like a weather model or economics model in economics, where you plug in, you create the model and you plug in all the variables like fecundity, number of eggs per female, number of hatchlings per female, number of fledglings per female, survival rate, what percentage of them survive to next year. And of course, that's death rate. Survival, death rate are two sides of the same coin. Probability of, and here's another thing, it's little things like, what's the probability of, you've got a bunch of kids, right? How many of those kids actually will eventually, next year will have a nest of their own? The probability of a helper inheriting a nest. By the way, there's lots of predators of red-cockaded woodpeckers. So yeah, mom and dad, one of them might only live about 2 or 3 years. Birds don't usually live more than about 2 or 3 years. And then you plug in the probability of catastrophic events, mainly hurricanes. And then you expect over time, your population is going to fluctuate over time like all populations do. That's not a problem at all if you have a large population. This is annual mortality rates for red-cockaded woodpeckers in North Carolina. Look at this. Look how much variation there is from year to year. These are different types of individuals, but depending on which category, which demographic category they look at, survival mortality rate, that's the annual mortality rate, could be as high as 70 to 80%. These are probably fledglings. So in other words, if you're a red-cockaded woodpecker and you successfully fledge this year, your chances of being around this time next year are only about 30%. Adults survive better. But even them, look at this, some years there's really good years with relatively low mortality, and some years it's pretty high. There's a general rule about for adult birds, there's only about a 50% chance of a wild bird surviving to the next year where small birds go. So you have to account for this. Why is this important? Because there's going to be pressure on you to delist your species and say, hey, you've done well enough, you have enough red-cockaded woodpeckers. They don't have to be, you don't need to have, your conservation efforts can go ahead and end now. And the population is sustaining with what it has. So how large do they have to be? So now what you want to do with your model is, well, what do you plug into it? Now you can go get the data, which we have. I chose the species because we have a lot of data on fecundity and survival rate, all those things, fledgling rate. But you got to plug in, what you want to do is you want to plug in what you start with. You need to be realistic, because what you're talking about here on the ground is, cases like Silver Lake. They have there's only so much land they can set aside here. Only so much land they can protect. These are NGOs, they depend on donations. So how much, what was their goal? They wanted 50 family groups. They're not there yet. You get 50 family groups, they're going to have to do a lot of habitat work. A lot of work sucking flying squirrels out of potential nests. Very hard. Can they actually do that with what they have here to work with? Look at these pine plantations all around. Well, so what what you want to do is you want to model it. So what they did in this study was to try to figure out, with all the great work that's been done with the conservation with red cockaded woodpeckers, is how much more do we need to do? How large does the population have to be? And we need to have conservative estimates to be safe on the safe side. You want to get the population up to an even higher level than you need to stay on the safe side. So this model is PVA model, and what was the goal? You want to have red cockaded woodpecker populations that are just running in the background. There's no danger of local extinction. And what does it take in order for this to happen? So this is an example here of a study where this was done. And let's look at the paper itself. So this is what you have here. We're seeing these different rows here. These are different arrangements of family groups around the landscape in this artificial population. So what I want you to focus on in particular is right here, D500 and D250. D500 is where the habitat is so good that you can pack 500 territories within 768 square kilometers. Now, I could look that up and see what that is. There's that like 80, like over 80 kilometers by 80 kilometers. Am I thinking of this right? So it's a large area. So this is they just started off modeling like this. This is not a realistic case, but to say, anyway, it's a large area. I'm not going to try to draw it out, but so this would be over a large area, kind of like this right here. So within that area, this is what they're modeling here. Within an area there, how many are you able actually, you're just asking the question, could a population like this survive in the future? Because this is kind of the best case scenario. If the answer is that they don't, then you have to say, it almost makes you wonder, like, well, is any of this going to work at all? But anyway, so in the model, it's 768 square kilometers. That's what they have to work with. So, imagine 77 kilometers by 10 kilometers. That's a big, big area. Now, within the area, what's the spacing like? Is it 250 territories within that area or 500 territories? 500 would be a really high quality habitat. 250, not, half the quality. So there's that. The other thing they looked at here, which I don't think we're really going to look at here in this class, is how clustered they are to each other. But let's just not worry about that right now. Let's just look at density. Okay. That said, the spacing is important because if these woodpeckers have to find each other, they have to, when they leave, they have to be able to find another nest. A male that eventually joins another family group, which does happen sometimes, he's got to be able to find that other family group. How far apart are they? So what they did was they modeled it with two different densities. And here's what they found. This is a really important thing to focus on here. So what you're seeing here is over here on the left-hand side is the number of territories surviving after 100 years. That is the percentage of territories surviving after 100 years you run this model, 100 simulated years. This is done over and over and over and over again, thousands and thousands of times simulated. What you want is 100% or more. That is, after 100 years, you have the same number you had before, but actually even more. That's what you want. So here's the target. You want that right here. Did they get that? And you see the arrows here. Yes, but under what circumstances? Well, if you can start off with about 50 territories, 49 territories, can you hit that 100 target? Well, what you're seeing right here is two different densities, ignore K, two different densities, 250 and 500. 500, I can tell you, is unrealistic. You're never going to be able to pack that many, have habitat that's quality enough to pack that many woodpeckers in. 250 is more realistic. So we could just look at 250 here, which are the little triangles. So the triangles with 49 nests, 49 family groups in this area, in this simulated area, is that enough? The answer is no. Look at this. Most, after 100 years, the population has declined by half. That's no good at all. What does that tell you? 50 is not enough. What does that tell you about? So this is just one area here, but imagine you have a bunch of different Silver Lake management area type efforts in one area. 50 family groups, not enough. Now, however, if there were some other conserved areas around, they might be able to have enough. Okay, now if you could get that density up to 500 on an average, 500, double the density, then yes, there's a slight increase in population size over time. So instead, given that that's unrealistic, let's look over here. What if you were able to get up to 100? You've successfully basically created 100 territories using artificial nest boxes and all the things you do. Hooray, you got 100 nest woodpecker territories, family groups. You succeeded. Is that enough? And you can see it is. So I think the take-home message here is that, I'll look at these error bars too, is that 50 is probably not enough for an area, general area, that probably about like a third of the size of this county, Washington County. 50 is not enough. 100 might be. This is the kind of work you do to try to get a feel for how well are we doing and how much better do we need to do. And can we delist the species? It's far more complicated than this, but this is the idea. Now look at the error bars. What this represents is that the models have different results each time you run them. So they were all over the place. So unfortunately, sometimes some of the models are telling you something different. Just like when a hurricane is modeled and its track is modeled, sometimes, eventually it hit Fort Myers. Ian did, right? But there were other runs that had it hitting Tallahassee or Tampa or missing Florida altogether. Just the nature of modeling. Anyway, what's the take-home message here? You need a lot of red-cockaded woodpecker nests, which are probably going to be very difficult to get. And much of it depends also on the density of the territories. Why does that matter? The reason it matters is because the birds have to find each other. And you see family groups don't get along, right? However, family groups have to start from somewhere, right? So what really happens is an individual will leave one family group, a young one, and go and find another family group to join. And then sometimes it's accepted. Or sometimes she just takes over. Anyway, or it'll start a new family group. But those habitat patches over the landscape, they need to be close enough to each other that the birds can find them. So imagine you are a bird, a red-cockaded woodpecker, a young male, and you find after 2 years or 3 years you've left. Who knows what they're actually thinking, but so you leave and you disperse and you fly. And off you fly 5 kilometers, 6 kilometers, 8 kilometers. You keep going. How far do you go? Maybe you end up flying 18 kilometers. And for whatever reason you flew in this direction. Are you going to find anything worth stopping at? I don't know what this is right here. Are any of these trees you see here, are they acceptable? Is any of this red-cockaded woodpecker habitat? I'm sure the answer is no. There is no red-cockaded woodpecker habitat anywhere in here. This is not like common species of woodpecker that'll nest in any tree. Red-cockaded woodpeckers, you could probably, drive for a month and not find any red-cockaded woodpecker habitat that's not already known about. It's so stringent and so strict what they need. So in other words, how do you ever get a population to actually grow out if the birds, if the habitat patches are all spaced out from each other and the birds can't find them? See what I mean? So density of habitat patches matters. And so higher density territory, a higher density of different territories means birds, they're closer to each other. Another reason why this is important is because sometimes one of those family groups will die out. So how quickly will those trees they were in be recolonized? Depends on how far apart they are. That's why density is important. Okay, so hope you understand why density is important. So here's, in some, you can get by with smaller minimal viable population size, fewer territories, if territories are more closely clustered within that area. But that means having in any given area lots of good trees fairly near each other. By the way, they also threw into this model an occasional hurricane type of event that kills, kill 20% of the population. The territories are close to each other. There are more potential dispersers, so that when one family group gets killed off or just dies out, that area gets more quickly recolonized. We don't think of it with a species that's not in danger. We don't think about any of this stuff. Like ephemeral ponds and North Woods, every year there's frogs breeding in them because the frogs are able to find them because there's so many ephemeral ponds and they're all close to each other. In endangered species, the habitat that's left that they need is all spaced out over a landscape so widely that individuals that leave don't know where they are and can't get to them. Keep in mind that individuals, when they fly or move through landscapes, they don't know what's over the horizon. I just want to point out, this is a special case of a bird that is a communal breeding bird, which is helpful when you're trying to conserve birds. They're tolerant of people going in there and manipulating them. They're not scared of people at all, really. They have the backup breeders in case one dies. Their population biology is really well known. And so this is actually a rare case of a lot being known about a species that actually can be studied really intensively. Unfortunately, they are weak dispersers. So when that scenario, I pointed out the possibility of one bird taking off, flying 20, 30 kilometers across a landscape looking for new habitat. It doesn't happen very often. Like I said before, on average, in any given year, the kids from last year, they're generally hanging around the same area. So once you get a bunch of red-cockaded woodpeckers here, they don't spread themselves out. They don't move very much. So imagine you want to set up, I don't know what's going on right here, but imagine you as a landowner here, you enter into a conservation program and say, I'm going to make this red-cockaded woodpecker habitat. How long will it take for red-cockaded woodpeckers to find that habitat? Will you actually have to physically bring them in? Well, it depends on how far it is. If it's that close, then yeah, they're going to find them. But these aren't like barn swallows that fly around hundreds of miles every year, thousands of miles every year. They tend to stay home. That's a challenge. So what do you have to do? That means you have to do translocations, like we saw in the video there. They have to capture them, try to get them to actually, I think they literally physically put them in a nest that was created, covered it up, and then in the morning let them out and hope that they'll actually like that nest. Anyway, it's hard doing translocations with birds because they fly, right? The tendency for animals to go back to where you took them from. The people I know that will catch a woodchuck under their cabin, it's giving them trouble, drive it a mile away. If it's a male, it's probably going to, actually, if it's a female adult, she's going to probably be back the next day. But red-cockaded woodpeckers, they don't go very far. So you look at how far they go. Well, here it is. I said we knew a lot about red-cockaded woodpeckers. Well, look at this. Distance from natal territories. These are the rare, these are studies where they actually had observations. So they put bands on the legs, on the feet actually of birds, and then they captured them later on. And so they knew how far out they went. So if you look at all of those cases where how far they actually dispersed, so these are all cases where males or females did finally leave home to start their own nest or to join another group. How far did they go? This is how far they went. This is proportion of all the observations. As you can see, the vast majority of them, whether males or females here, these are helpers that later became nesters of their own, stay at home and then they leave. Most of them only dispersed between 0, that means they stayed home, and 2 kilometers. So if you want red-cockaded woodpeckers to spread throughout the landscape of, say, Arkansas or Oklahoma, you're probably going to have to physically move them because it's going to take them too long, that population too long to spread. Same with females. However, notice this. There are a few individuals who went out as far as 9 kilometers, or 7 or 8. So they can go a few kilometers. They just don't do it very often. When they go out and fly around, we don't know what they're thinking. A bird's thinking. But when they fly out here, the bird will, when a male or female was a helper and now is searching for a new nest, or to join another nest, or to intrude itself on another nest, they search. But will they find? What will they find? Well, it depends on how many territories there are around to find. So in sum, I think now I hope you have a feel for what the modeling is about. It's a scenario. How large do we need to get this population up to say we've done a good job and now this population is now self-sustaining? That's the question. And the only way to do that is to model it because we can't really look ahead in time to see what's going to happen. In the case of the red-cockaded woodpecker, it's kind of discouraging because it looks like you have to have a lot of individuals and you got to have them all fairly closely packed, which means, and by the way, the red-cockaded woodpeckers will tolerate having other family groups nearby as long as their area they're in is really good. So the better the habitat, the more territories, the more family groups you can pack in there. But if each family group has to spread way out, then you can't have as many birds in the area, which means you effectively have fewer birds. Okay, so that's the introduction to populations so far, and we'll continue next week, hopefully in person.